When a rainstorm clears and a massive arc of color stretches across the sky, it can appear as an object anchored in the clouds. But to understand the source of those colors, we have to look past the horizon and focus on a single floating droplet of water. A rainbow is a continuous optical event. It requires millions of individual water droplets repeating the exact same physical sequence simultaneously. By tracing the specific four-step sequence within a single drop, we can identify the exact physical requirements needed to produce this light. Understanding this process allows an observer to predict exactly where and when these colors will appear. The process begins with sunlight. In the open air, this white light travels at its maximum speed along a straight trajectory. This diagram shows a cross-section of a single water droplet. Here, a beam of sunlight strikes the outer boundary of the sphere. As the light enters the water, it slows down. This change in speed causes the beam to bend inward, a process called refraction. This bend initiates the second stage, dispersion. Sunlight is a composite of 7 distinct colors. Inside the drop, these colors begin to separate into a diverging fan. Each color bends at a slightly different angle. Red light resists the bend more than the others, while violet is forced into the sharpest curve. The droplet acts as a natural prism, organizing sunlight into a predictable sequence of wavelengths. This separated spectrum travels through the drop until it impacts the inner back wall. Usually, light passes through water, but at this specific angle, the back of the droplet acts like a mirror. The light reflects back into the interior, a process known as total internal reflection. Because the light is reflecting backward, you only see a rainbow when you are positioned between the sun and the rain. Finally, the light reaches the front of the drop again. It exits the water, bending one last time as it moves back into the air. This second bend fixes the exit angles, projecting the colors in a widened arc toward the ground. Without this precise sequence, the entry, the internal reflection, and the final exit, the light would scatter and the sky would remain gray. To see this result in the real world, we have to look at the geometry between the rain and the observer. There are 2 spatial requirements. First, the sun must be at your back, shining directly into the rain ahead of you. Second, there must be a concentrated field of falling mist or rain in front of you to act as the reflecting medium. This diagram shows the final angles. To reach the eye, red light exits at 42 degrees and violet at 40 degrees. When you look up, you search for this narrow window where light from millions of drops converges into a visible band. Because red light always arrives at the highest angle, it forms the outer edge of the arc, while violet always forms the inner edge. A rainbow is not a physical object in the sky. It is the result of a specific geometric alignment between the sun, the rain, and the observer's line of sight.